All right, so moving right along here in Chapter 8, we've set the stage. We've talked about some key ideas about solution behavior, solutes and solvents, and then electrolytes and non-electrolytes. So now we're ready to move even further and start to explain some of those issues that have already crept up if you've been paying attention, like silver chloride being an ionic substance that's not soluble in water. So that idea of solubility, that's what we'll talk about in this section of Chapter 8, and we'll learn at least how to predict which substances we expect to be soluble in a solvent like water, and then learn some exceptions to those rules. Now, in addition to solubility talking about whether or not something will dissolve in the first place, it's also a quantitative as well as a qualitative idea. So solubility not only describes will it dissolve or not, but how much will dissolve. And technically, solubility, when used in this way, is the amount of solute that dissolves in a specific amount of solvent at a given temperature, and so it's already affected by temperature we see and amount. We also have the type of solvent and its temperature there, and it's expressed as grams of solute per 100 grams of solvent. And in our course this semester it's usually water, but in 142 we might talk about a few non-aqueous systems as we deal with the organic chemistry end of that organic and biochemistry topic. All right, so we go right into talking about grams of solute per 100 grams of solvent as being the definition of solubility, and then we go back to that vague qualitative idea here with unsaturated solutions. So an unsaturated solution contains less than the maximum amount of solute. So it can describe a solution that has just a very small amount of solute or almost up to the maximum, but just below it. And there's actually a fairly simple test to see if a solution is saturated or unsaturated, and that is to add a little more solute. If it dissolves, then the solution was unsaturated before you added that solute. Now maybe it's saturated. We don't know. We'd have to add a little more to see if that dissolves. But if you add solute and no more will go into solution at the given conditions, then you know you must be saturated. So there we have it. A saturated solution, on the other hand, has the maximum amount of solute that can dissolve in the solvent. So therefore, if you add additional solute, it will not dissolve in that amount of solvent at that temperature. We also have to consider the rate at which that solute dissolves, because it may look like there's nothing happening, but really in a saturated solution, we have some solute dissolving, but other solute reforming at the same rate. So that's what's really going on. It doesn't look like there's a net change at our naked eye level, but at the level of atoms, we have some solute dissolving, but other solute recrystallizing, and no net change in a saturated solution. So if you have a saturated solution with some undissolved solute at the bottom, then you've got this dynamic process that results in no net change, but you do have dissolution and recrystallization happening at exactly the same rate. Before we get too far along, let's pause here for a learning check. So at 40 degrees Celsius, the solubility of KBr, potassium bromide, is 80 grams per 100 grams of water. Identify the following solutions as either saturated with an S or unsaturated with a U, and then just explain your reasoning there. So in the first case, we have 200 grams of KBr added to 200 grams of water at 40 degrees Celsius. And then in the second instance, we have 25 grams of KBr added to 50 grams of water at 40 degrees Celsius. So pause the video here, identify each of those as either saturated or unsaturated, and make sure to justify that answer. When you're all set, start us back up and we'll see how you did. All right, so in the first case, we are indeed saturated, right? Since we said the solubility at 40 degrees Celsius is 80 grams per 100 grams, then if we had 200 grams of water, the maximum we could have is 160 grams of KBr. So having 200 grams of KBr in the 200 grams of water, we're over that solubility limit. In the second case, we're actually unsaturated because if we had the 25 grams of KBr added to 50 grams of water at 40 degrees Celsius, well, if we have 80 grams dissolving per 100 grams of water, then we'd have 40 grams could dissolve in 50 grams of water, and we have less than 40 grams of KBr here with just the 25 grams of KBr. So in this case, we must be unsaturated, and hopefully you had relatively little trouble identifying each of those correctly for those reasons. If it didn't go well, then please do try some additional problems and certainly reach out to me if I can be of assistance. Now, we've already mentioned that temperature does play a role in this, and hopefully you noticed in that learning check that we were specific about temperature because those were the solubilities for 40 degrees Celsius. The solubility of KBr is probably temperature dependent, and it might go up or down with an increase or decrease in temperature. Unfortunately, we can't say without exception that solubility increases or decreases with temperature. By and large, the rule of thumb is that the solubility of most solids increases as the temperature of the solvent increases, and we could say the opposite tends to happen for gases. The solubility of gases decreases as temperature increases. If you think about your soda, if you leave soda out at room temperature for very long, it will go flat because the higher temperature will allow for more of that carbon dioxide to escape because it's less soluble at the higher temperature. So you want to pour it and get the bottle back in the fridge ASAP so that you don't lose too much of the gases. And that tends to be a pretty safe rule, that gas solubility decreases as temperature increases. You don't even have to have something artificial like carbonated water and soda. If you happen to like a cold glass of water at your bedside at night, you probably notice in the morning that there's lots of little bubbles, and that's just the dissolved nitrogen and oxygen from the atmosphere coming out at that slightly higher room temperature compared with the temperature of the cold water. So that tends to be pretty uniform. The solids, it's a little bit trickier because if you look at our graphic there, NaCl is fairly independent of temperature. Its solubility increases a little bit as you go from, say, 0 to 100 degrees Celsius water, but it's right around that 40 grams per 100 grams solubility. If we look at other substances like sodium phosphate or glucose or really anything else, the solubility is much more temperature dependent, and there are even substances like calcium acetate, for instance, where the solubility goes down as temperature increases for that solid. So solids are a little less predictable. Gases tend to behave in that way, that gas solubility decreases as temperature increases. Most solids have the reverse, where solid solubility increases as temperature increases. But again, that increase can be very different for different solids, and sometimes you even have solids like that calcium acetate where the solubility actually will decrease with an increase in temperature. So if solids are so unreliable, I guess is the best way to refer to it, why are gases so reliable here with solubility and the amount of gas that can dissolve? Well, Henry's law gives us the answer there, and Henry's law states that the solubility of gas in a liquid is directly related to the pressure of that gas above the liquid. So at higher pressures, more gas molecules dissolve in the liquid, and if you think about it, either in a closed container where you can control the amount of gas, then not too much can escape. In an open container now, some can escape, and if you have warmer conditions, more of those gas molecules can escape. They can move away faster, and that's why you have a greater, a higher temperature of solvent rather gives rise to more gas escaping there as solute. So Henry's law specifically is about solubility and pressure, but it does also help us maybe to have a picture in our head as to understand why temperature increase in the solvent causes gas particles to escape at a faster rate and therefore have a lower solubility. Before we go too far, let's take another learning check opportunity here, and we've got a couple questions for you to think about and respond to. First, why could a bottle of carbonated drink possibly burst or explode when it is left out in the hot sun? And second, why do fish die in water that is too warm? There's unfortunately a number of examples of these fish kills where you get large numbers of fish dying, and unfortunately it's often industrial heat that's the responsible cause. The industrial heat, hot water from industry warms the water too much and the fish die. So why might that be? Go ahead, pause the video here, take a moment to respond to each of those, and start us back up, and we'll see if you came up with the same reasons that I did for this learning check. Okay, in the first case, well, we've already talked about the idea that gases, almost without exception, have lower solubilities at high temperatures and therefore leave the solution. And so as that happens, of course, in a closed container, the pressure inside the container increases, and depending on the strength of the bottle, it could burst, especially if it has a weak spot or whatever, it's been dropped previously. So it's not common, but it is possible, depending on how hot it is and how much gas is dissolved in there, that you could have the container fail because of that increased pressure from the gases becoming less soluble as the solvent there, the solution, becomes hotter. And the second case, why do fish die in water that's too warm? Well, again, fish rely on dissolved oxygen. That's how they get their oxygen. They have most fish have very sophisticated gill systems that can extract that oxygen. But if that oxygen amount goes too low, then the fish aren't able to get the oxygen they need and they die. And so if the O2 gas is less soluble because the water has warmed too high, then the fish can't get enough O2 to survive and they will die. And like I said, unfortunately, sometimes these things happen as a result of industry dumping water that's too warm back into an area that's too close to the fish, and that will cause these fish kills. That doesn't happen in the U.S. very much anymore because we know about that, but in the developing world, it's sometimes still a problem. Okay, so although we've defined solubility as a quantitative thing, we can also think about it qualitatively. And so sometimes salts are soluble, and on rare occasions salts are insoluble in water. And the reason for that is to do with energetics, as we've already mentioned here in the solutions chapter. If you don't get more energy out of hydrating those cations and anions from the ionic substance dissolving than is necessary to overcome the ionic bonding, then it just won't happen. So ionic compounds that dissolve in water are called soluble salts, and this tends to be the overwhelming majority of salts that we encounter are soluble. However, there are ionic compounds that do not dissolve in water, and those are known as insoluble salts. They might dissolve in a different solvent, and to be honest, they dissolve to a very, very small extent in water, but at least in terms of appreciable, measurable amounts, we'll call them insoluble. And one of the main types of reactions, if you think back to our chemical reactions, we had precipitation reactions. Those were the result of mixing certain aqueous solutions, certain soluble salts together to produce insoluble salts. So we've already seen this, but now we're going to have some rules and some ability to predict when we might encounter one of these insoluble salts as opposed to the more common soluble salts. All right, again, I have said it multiple times. I'm not for a whole lot of memorization, but there's certain times you just can't avoid it. So the solubility rules are one of those times where you really do just have to commit it to memory. And there's not a whole lot of rules, so hopefully you catch on quickly and it's not terribly taxing. If your memory's getting like mine, then maybe this will be more challenging than it would be to others. But again, do your best and just try to remember these few simple rules, and you'll have pretty good predictive power about solubility. So first and foremost, soluble salts typically contain at least one ion from group 1A, so the metals there. So of course hydrogen's in group 1A or group 1, but doesn't fully fit there because it's not a metal. Starting with lithium on down, those are the ions we tend to be talking about. The nitrate ion is one of the polyatomics that tends to give rise to soluble salts, as does the ammonium ion, our one polyatomic cation, which behaves a lot like potassium, which is a group 1A, or the acetate ion. Those ions almost exclusively give soluble salts. At least anytime you'd encounter it in this course, anything with those would be soluble. Most other combinations we'll consider to be insoluble, although that's not always true, but sometimes we will encounter that. So like chloride, bromide, and iodine, for instance, would be insoluble if it were paired with silver, lead 2+, or mercury 2, 2+, the dimercury ion. Sulfates tend to be soluble except when you've got lower group 2, so calcium, strontium, barium, the lower members of group 2 there, or if you've got it paired with lead ion, which we've already said lead can give rise to solubility issues in the previous chloride, bromide, iodide case. And then finally, if you've got the carbonate ion, the sulfide ion, the phosphate ion, the hydroxide ion, those tend to be insoluble unless we've got, say, lithium carbonate or ammonium sulfide, that group 1 and lithium on down and ammonium. If you've got those cations, no matter what the anion they're paired with, they'll always be soluble. So unfortunately, the rules aren't always hard and fast, but if you get used to these, you'll probably be able to predict in most cases when you would expect something to be soluble in water versus an ionic solid that might be insoluble. And again, the giveaway tends to be either silver, mercury, lead, or those lower group 2 cations, or anions like carbonate, sulfide, phosphate, or hydroxide. All right, and here we see in table 8.9 how we use the solubility rules. So if we have an ionic compound like potassium sulfide, well, what would we expect? It's got that sulfide ion, which is usually insoluble, but then again, we've got the potassium ion, which is usually soluble. So in this case, that group 1A potassium ion is the more important feature, and therefore we're going to be soluble in water because of that potassium ion. In the case of calcium nitrate, well, the calcium ion we know is sometimes insoluble, particularly when it's paired with things like sulfate. But here the nitrate ion is always soluble, so we would say that this should be soluble in water. Lead 2 chloride, well, that was one of our examples of an insoluble chloride. As we said, lead, mercury 2 plus, or silver, so therefore our reasoning is that it's something that's insoluble with chloride is the lead ion. Sodium hydroxide, we said that most hydroxides are insoluble, but again, sodium's a group 1, so that trumps the hydroxide's general insolubility, and so we do have a soluble salt here because it contains the sodium ion. And then finally, aluminum phosphate. Our rule for phosphate was phosphates are generally insoluble unless we had a group 1A or ammonia ion, and aluminum is neither of those, so therefore we'd expect the phosphate rule of usually being insoluble to hold here, and we have an insoluble salt because we have no soluble ions. So hopefully that gives you the flavor for this. Of course, we're not going to leave it there. We're going to follow up here with a learning check. All right, so in this learning check, you will use the solubility rules to determine if each salt is soluble or insoluble, and then you'll explain your answer. So go ahead, pause the video here, try to do this on your own as much as possible. If you need to peek at those solubility rules for the first couple just because they're new to you, go ahead, but please do try, based on what we've just discussed, to do it without any special aids. You won't have the solubility rules available to you come exam time, so the faster you get used to them, the better. All right, and hopefully you came up with these same results that show on the screen now. For the sodium sulfate, it's a soluble salt because it contains the sodium ion, one of the group 1As. For magnesium carbonate, we'd expect that to be insoluble because we said carbonates usually are, and there's no group 1A or ammonium ion to make us believe otherwise. For number 3, well, we've already seen that example, so hopefully you didn't even have to think about that one too hard, because lead as a chloride, an iodide, a bromide is insoluble. And for the last case, magnesium chloride, we'd expect it to be soluble because it was not one of our exceptions, right? The chlorides of lead 2 plus, silver plus, and mercury 2 plus are the insoluble examples. So because because magnesium is not one of those lead, mercury, or silver examples, we'd expect it to be soluble. So hopefully you were able to get this. If not, I'm guessing it's just for lack of practice, and please do spend some time with those solubility rules and some time practicing some other examples so that you get the hang of it. So now that we're getting used to these solubility rules, hopefully you've familiarized yourself with them already, we can predict the formation of a solid. So not only can we predict whether or not a given substance is soluble to begin with, if we say that we have a solution of two substances, then when we mix those two separate solutions, which we know must be soluble if they've formed aqueous solutions, what about the products? Will everything stay soluble, or will some of those species come together to form insoluble precipitates? So if we look at this example here, if we have silver nitrate, which we know silver can be problematic, but all nitrates are soluble, so silver nitrates forms a nice aqueous solution, so that's in one of our test tubes. And we add some sodium chloride, a table salt, which we know dissolves quite well in water. Well, individually, those two substances are soluble in water, but what about the products they might make? Well, looking at a reaction like this, the only thing we can really do is swap anions and cations, right? That's about all we can do. And if we swap the anions and cations and they're still all soluble species, then we say no reaction happened. But if we swap the anions and cations and we end up with at least one insoluble substance, then we have a precipitation reaction, and we will write it as you see here. So we know that silver nitrate is soluble and sodium chloride is soluble, but when we combine those two soluble species, we get sodium nitrate, again, super soluble, right? All sodium salts are soluble because sodium is a group 1A cation. All nitrates are soluble because of that same rule in our solubility rules. So sodium nitrate would stay in aqueous solution quite well, but silver now would pair with the chloride ion, and we already know that that's one of our exceptions. Silver chloride forms an insoluble salt. That's one of our examples of an insoluble chloride, and therefore we would indicate a solid for the silver chloride. So that's our precipitate, and then we continue to keep the sodium nitrate in aqueous solution. So what we just experienced there with the silver nitrate and sodium chloride combining, that was called a full equation, sometimes called a molecular equation, depending on the text that you might see. So a full equation shows the formulas of the compounds. Here's a different example with lead nitrate and sodium chloride combining to form lead chloride. Again, another of our insoluble chlorides. So lead 2 chloride does not dissolve in water, so that forms a solid precipitate, and then the sodium nitrate stays in solution. If instead of writing it like it's a molecular species, because it's not, right? These are ionic substances, we can show a complete ionic equation, which shows all the ions. So we have the lead 2 plus the 2 nitrate ions, plus the 2 sodium ions, plus the 2 chloride ions, forming now that lead chloride. We can't break that one up because it doesn't break up in water, right? It is a solid, so it doesn't stay those free ions in water, but we do still have the 2 sodium ions and the 2 nitrate ions pairing with each other or rather pairing with water in aqueous solution. So finally, if we want to just show the net ionic equation, which shows only the things that change from left to right, we can look at the complete ionic equation there in the middle of the slide, and we see that all the bolded species are what change from left to right of the arrow. The 2 nitrate ions and the 2 sodium ions are present in aqueous solution on both the reactant and product side, so they cancel out, and we're left with a net ionic equation that's just the lead 2 plus ion in aqueous solution plus the 2 chloride ions in aqueous solution, yielding the lead 2 chloride solid, which will not dissolve in water. Okay, so the net ionic equation is usually what we're after, although it's important that you be able to write each type of equation that we have for solid forming reactions. So we worked it together, but now let's just make it a little more explicit. If we want to write the formation of equations where we have an insoluble salt form, a precipitation reaction, we have a few steps there. And in the first step, we write the ions of the reactants. In the second step, we write the combination of ions. So we swap cation and anion pairs and determine if any are insoluble. We write the ionic equation, including any solid. And then in the last step, we write the net ionic equation, which if no solid was formed, there'd be no net ionic equation and therefore no reaction. If we do form a solid because some insoluble species is produced, then we would have a net ionic equation, and that's usually what we're after. So let's see how well you can apply those steps in this learning check. So when solutions of sodium carbonate and barium nitrate are mixed, a white solid forms. Write the ionic and not ionic equations for this reaction. So go ahead and stop the video here. Take your time. You could even start at the molecular or the full equation and then work to the complete ionic and then net ionic equations if you choose. But again, at least the ionic and net ionic equations, and then start back up and see how you did there. Okay, good luck. All right, so in step one, we're going to swap partners, right? That's how we're going to see if we end up with anything that's going to be insoluble in water. So we take our barium nitrate, break it up into the 1 mole of barium 2 plus ions and the 2 moles of nitrate ions. And we also take our sodium carbonate and break that up to the 2 moles of sodium ions and the 1 mole of carbonate 2 minus ions. And now we'll swap partners. We'll exchange cation and anion pairs and see if we end up with anything that would be insoluble. Okay, so in step two, we're going to write the combination of ions and determine if any are insoluble. So we took that sodium carbonate and the barium nitrate, which each was individually soluble in water. And when we combine those two soluble solutions, we would find that we make sodium nitrate, which is indeed soluble. All group 1 or 1A cations, and sodium's an example there, would be soluble, as well as all nitrates are soluble. When we take the barium 2 plus and the carbonate 2 minus, unfortunately we don't get a soluble result, right? Most carbonates are insoluble aside from group 1A and ammonium ions. So barium is neither of those. So as a carbonate, we'd expect it to be insoluble, as is the general rule. And therefore now we do have a precipitation reaction because we're going to form solid barium carbonate. Now in step 3, we can write the ionic equation, including any insoluble solid. So we have Ba2 plus aqueous plus 2NO3 1 minus aqueous plus 2Na plus aqueous plus CO3 2 minus aqueous yields the barium carbonate solid that we know is insoluble by the solubility rules, plus 2 moles of nitrate ion aqueous plus 2 moles of sodium ion aqueous. So now in step 4, we can write the net ionic equation by deleting these spectator ions. That's what we call the ions that appear in the same way on both sides. So the 2 moles of nitrate ion, it appears as 2NO3 minus aqueous on both the reactant and product side of the arrow. Likewise, the 2 moles of Na plus aqueous appears in the same form on both sides of the arrow. So we'll eliminate those and we're left with Ba2 plus aqueous plus CO3 2 minus aqueous yields BaCO3 solid. So that's our net ionic equation. We do indeed have a precipitation reaction, and hopefully that's exactly what you arrived at on your own in this learning check. If not, please do try some additional examples. There's lots of these in the book, and certainly if you get in touch with me, I can give you more examples to work and more advice if you're running into trouble. Otherwise, hopefully things are all going well, and I'll see you for the next section of Chapter 8.